People in 201. This is Maps and Hash Code, compsci 201, September 18th. Hopefully I'm delivering this to you actually in person via Zoom, but just in case, here's the video of class. G is for Git, the quintessential version control system that we use in 201. G is also for GNU, sometimes pronounced GNU. It's an acronym that's self-referential. GNU is not Unix. It's what became Linux, and it drives more computers than any other operating system in the world. G is also for Google, perhaps the most and best example of a disruptive innovation. We're seeing ChatGPT, which might follow in its footsteps. This week in 201, APTs are due Wednesday. That's always the case. You should already know the APIs and the concepts needed to do these. There is always a 24-hour grace period, which applies to P1, N-body, which is out and due Wednesday. As with all projects, as you see, there's the 24-hour grace period. P2 will go out after that is due. It will be due October 2nd. That's a change on the calendar. You should see it now. And as a reminder, there's a midterm on October 4th. Policy for the midterm: in class, you'll need a writing utensil. You may not use any electronics. You can bring 6 pages, that's 3 front and back, of notes that you decide what they are. You will need your name on that, and you'll need to turn it in. I'll remind you of this again, and I'll give you a small sample midterm to give you an idea of what that midterm will be like. Again, as a reminder, we call these midterms. There are 3 of them. And when you do the mandatory final, the best score from your midterm and that portion of the final that's about those questions will be the one that counts. So the final can't hurt you, the midterm can't hurt you. You get a chance to try twice essentially for each set of concepts. All right, today in 201, we're going to try to understand hashing in general and maps in particular. Hashing, as I've mentioned before, is a constant time lookup, which is amazing. We'll also see how list, set, and map are part of the Java collections interface and the collections set of classes. I'll try to say some more about interfaces and make sure that I emphasize that understanding interfaces and inheritance is not an essential part of 201. And I hope we'll get more accustomed to Java programming in the context of solving specific problems, and we'll see that again in class on Wednesday. Interfaces and inheritance. Just as a reminder, interfaces are the name of a class, actually an interface, not a class, that provides methods and typically a contract or specification about what those methods mean and how they interact. We'll see an example on the next slide. Interfaces can contain no state or instance variables. Interfaces can have what are called default implementations that those classes that implement the interface can have. Implements is what's used for interface. A class implements an interface. For example, ArrayList implements list. Extends is what's used for inheritance, and we've also seen that. An ArrayList is a list, and an ArrayList is a collection. We usually use that phrase is a in discussing inheritance and interfaces in object-oriented programming. Now, it's not something that comes easily, the understanding of implements and extends. I'll show some more examples, but it becomes clearer over time and more coding. The key thing here is do not worry or stress, or even perhaps think about the differences between interfaces and inheritance. You will see them in the projects we do, but a deep understanding of them is not essential for thriving in compsci 201. Here is an example of the collection interface, and we'll see how that's used for lists, sets, and today maps. And one thing of note is that this interface collection extends another interface, iterable. I'll remind you of what iterable is soon. We can see here from the Java doc, the documentation that's associated with the collection interface. The root interface in the collection hierarchy. A collection represents a group of objects, known as its elements. Some collections allow duplicate elements and others do not. Some are ordered and others are unordered. The JDK, the Java Development Kit, does not provide any direct implementations of this interface. It provides implementations of more specific sub-interfaces like set and list. This interface is typically used to pass collections around and manipulate them where maximum generality is desired, and we'll see that in some parameters soon. Here are some methods of all classes that implement the collection interface, typically one of its sub-interfaces. You can see add, all, clear, contains. There are many. I'm just going to blow some of those up. Add all, clear, contains, and contains all. All of those are methods of the collection interface. And we'll see soon an example of how the implementation of one of these methods can allow implementation of the others. So, how does this collection interface work? We will see linked list soon. We've already seen ArrayList. Those are classes that implement the list interface, which in turn implements the collection interface. We have seen HashSet. We will now today understand how it works, and we will soon see TreeSet. Those are classes that implement the set interface. And today we will see HashMap, a new class that implements the map interface, which in turn implements the collection interface, which means they have add all, contains all. So let's take a look at the differences between some of these classes. Both ArrayList and HashSet have a constant time .add method. In the ArrayList class, it simply adds a new element to the end. But in a HashSet class, it has to make sure that there are no duplicates. So first it has to determine whether that element being added already exists. And it does that in constant time. For the ArrayList contains method, the code must search through all elements in the underlying array. That's linear time, meaning as the size of the array scales, the time it takes to run contains scales in a linear way. HashSet is different. Contains works in constant time. That means whether there are 1, 10, 1,000, or 1 billion elements in the set, determining whether a hash set contains a specific element takes the same amount of time, constant time, regardless of the size of the set. As we saw earlier, the collection interface extends the iterator interface, the iterable interface. That's a winner in terms of coding because iterators have hasNext and next methods to iterate over all elements in a collection, the same way we've seen hasNext and next used to iterate over a scanner. Let's look at some code to see an example of that. This is the code for add all in the open source AbstractCollection class. We can see that there's a parameter, and if we look carefully on line 4, you'll see that the parameter has type capital C collection and then an angle bracket. The name of the parameter is collection. Then we see the code, and in particular, we can see that on line 6, that parameter collection must have an iterator method that supplies an iterator because it's a collection, capital C, which extends the iterable interface. And then we see the iterator used, hasNext and next, to iterate over all elements of the collection parameter. And for each of those elements, the add method is called. So this code exists in the AbstractCollection class, and it's the same code for a set or an array list or a map. The difference is that add is implemented differently in each of those classes. The list.add method, as a reminder, simply adds it to the end of the list. The HashSet add method has to first search for the object being added and only add it when it's new. We can see here that add and add all both return a Boolean value. Typically, those values are ignored in the code you write. When you call add for an array list, it's going to succeed. Add for a set is different because adding an element to a set will return false because it won't be added if it's already there. For this AbstractCollection class, It implements the collection interface, but in each of the classes that implement that interface, such as list and set, methods are done differently. Some code is in this AbstractCollection class, like addAll, and that code is implemented using other methods like add. As to reiterate, list and set use the same addAll method. They have very different add methods. This inheritance and interfaces have an abstraction level that allows one method to be implemented in terms of another and helps coding. It's a great way of trying to understand and develop your own intuition and skills. Time for a WOTO. You should pause the video, complete the WOTO, and then we'll be on to the next subject. We're going to try to understand hashing, and here's some analogies. If you do a reverse image search, either using Google or a company called TinEye, it takes that image, converts it into a number, and then looks up that number, essentially, to determine if other images are similar. The same thing happens when you convert sound to a number. You might have used SoundHound or Shazam to try to locate what the name of some music or a tune is that you're listening to someplace. YouTube and TikTok use this same idea to be able to put ads up for particular music, or to recognize whether the music being used in a TikTok video or a YouTube video are copyrighted and what the copyright holder wants to do. In order to look those up, either images or sounds, you have to convert them to a number. The same thing happens with a hash set. We need to convert an object to a number, and then we use that number to look up the object in the set. So one analogy that we often use in 201 is that there's a set of lockers or boxes. You may have had a locker in high school. It likely had a number on it. You have a box at Duke that your mail comes in. The idea is that you ask an object what its locker number is, and you do that by calling the object's hashcode method, because every object has a hashcode method. And that's designed to return the locker or number of where that object is supposed to go. Now you have to open that locker or box number and look inside it to see if the object's actually there. And you find it or determine that the object's there using the .equals method. So let's explain that in a little more detail. Every object has a hashcode method because every class in Java descends from the Uber class capital O object. The idea is that different objects will return different hash values, so that the string hello and the string goodbye return different values because they're going to be in different lockers. Now sometimes things aren't ideal. It's not actually possible for every object, for example every string, to return a different locker number, because you have to be able to determine these numbers quickly. So we'll write code to cope with when two things end up in the same locker, and we'll see that it's the equals method that allows us to do that. So each locker, sometimes we call them buckets, contain all the objects that have that same locker or bucket number, that same hash value. In sets and maps, there's an array of lists where each array index is a list associated with that locker or bucket. So each locker contains a list of the things in that locker. We're going to see a diagram and some pictures to help understand that. There are going to be these so-called hash collisions, meaning two different strings or two different objects end up in the same locker, the same bucket, the list associated with that locker number. So in this diagram, and these are hypothetical, we're showing cat and hello both in bucket or locker 1. So there's a list of the things in that bucket. We're showing dog and world both in the list associated with locker or bucket number 4. Now, how did we determine that dog and world were in that bucket number 4? We called the hashcode method on those strings. We called the hashcode method on hello and cat. Now, The hash code range is huge. It returns an int. It could be somewhere between -2 billion and 2 billion. Now in our list here, our array of lists for our lockers, we only have 7 elements. So we'll have to use hash code mod 7, and we'll see we have to actually do something slightly different. So let's take a look at the code for what might happen when you're looking up something using this concept of hashing. First, we need to determine where to look, what locker or bucket an object will go in. We're going to, for the purposes of this example, assume that each locker, each bucket, stores a list, and we'll use an array list in the code. We're going to create a private instance variable for this locker array, this bucket list. And here's an example shown on line 15 where we've created an array. We can see that my buckets is an array because there are brackets to its left. And it's an array of array lists. Now it turns out in Java it's tricky to write the definition for an array of array lists. We see on the right hand side of that assignment operator, new array list bracket 100. We know that's an array, but typically when we see array list, we see the angle brackets for the type of thing in the array list. Now, for very deep programming language reasons, we can't do that in Java. And so we have this phrase on line 14 to suppress the warnings that it's an unchecked type. That doesn't really matter. It's just nice to know that our code will work without a red squiggle because we have this annotation of suppress warnings. We won't actually have to use this in 201. I'm just showing you this example of an array of lists so that we can try to understand how hashing works when we're looking something up. Here's a diagram. The URL shows where I found this diagram online. The key for hashing using this so-called hash table, that's the internal set of lockers or buckets. We take the key, could be a string, could be any object. We call its hash code method. That takes that key and turns it into a number. We can see in this machine diagram that you feed a key in at the top, you hash it or call its hash code method, and a number comes out at the bottom, that number 4. Now that means that that object, that key, is in the list associated with locker number 4. Now this diagram shows what we will learn in a couple of weeks is actually a linked list. It's another kind of list rather than an array list, but for our purposes it's a list because it's the list interface. Here's the code that would work to actually implement that diagram. We're going to write the contains method for what might be HashSet. The first thing we do is we find the locker or bucket number that the object that's the parameter to contains is in. So we call its hash code method. We can see that on line 18. We convert that to a positive number by calling math.abs, the absolute value, and then we mod that number by the number of buckets. Remember that mod, say 7, returns a number from 0 to 6, the remainder when you divide by 7. That makes it a valid bucket number. Then we iterate over all the elements in that bucket list, because remember, in every locker number and every bucket there is a list of the things in that locker. So we iterate over all of them, and if we find the one we're looking for, that's the parameter obj, is it equal to one of the things in this locker, then we return true. And if we iterate through all the things in that locker, eventually we'll return false. There are going to be more than one thing in each locker. There will be hash collisions. To show this in the real world, I wrote a program that just iterates over all the words in a very large list of words, calls hash code on each of them, and sees is there a duplicate. So we can see here that buzzards and write O both have the same large negative hash code value, and words that I'm not sure what they mean but are in this file of words, snits and unprecludable, have a very large hash code value. That illustrates that there will be collisions. As long as each locker has a small number of things, we get really good performance. And in practice, it turns out hashing works. Even in theory, it's going to turn out that hashing works most of the time. As long as your hash code distributes things evenly, you get very, very good performance, constant time performance. In order for this process to work, the code and the diagrams, it has to be the case that if A is equal to B, that means A dot equals B is true, then A and B must have the same hash code. Because if they have the same hash code and we want to determine if they're the same thing, we have to iterate through each one calling equals. We don't want A and B to be equal and end up in different lockers. We won't find them. So if A and B are equal, that means A dot equals B returns true. We also want the hash codes to be the same. Now the converse is not true. If the hash codes are the same, we can't determine, and in fact it's not necessarily true, that A dot equals B. Recall we saw that buzzards and write-o have the same hash codes, but they're not equal as strings. But if we had equal strings, we know they'll have the same hash code. Now, if we write code in which hash code just always returns 0, it will be correct, but slow, because every element will be in the same locker. That means the list in that locker will be really long. If we add 1,000 elements, they'll all go in locker 0. But it will be true that any two things that are equal will be in the same locker because they have the same hash code. That's a bad hashing function because it turns what should be a constant time search into a linear time search. Here's an example of how that works. If your hash code returns 0, everything will be in the list associated with locker or bucket number 0. We know that the Java toString method works in general to convert an object to a string. We also know that the string hash code method is really good because strings are hashed all the time. So there's been a great deal of effort put into making the hash code for strings distribute things evenly throughout the entire internal array of bucket lists. So one easy way of implementing hash code in a new class you write is to implement toString, and then whatever string is returned by that method, call its hash code. So this code shows a relatively straightforward way of making a reasonable hash code method, much better for sure than simply returning 0. Time for WOTO number 2. Now, we've understood hashing a little to see how hash sets work. We're going to look at another class called HashMaps and maps in general. This is a very common data structure used in a huge number of problems. In Python, it's called a dictionary. In C++, it's called a hash table. In PHP, it's called a hash. And the problem that we're going to solve is, given a file of words, determine how many times each word in that file occurs. And then we're going to print the words that occur often, like the most occurring words. So the idea is we might use Little Women by Louisa May Alcott, that's shown on the left here. Herman Melville has written both Moby Dick and Bartleby the Scrivener that are out of copyright, so we use those often. We can see that list of words in the middle. And then Frederick Douglass has written a book about bondage in terms of and slavery, and in his work we also see these common words. Notice that A and the appear in all these lists. How many times is going to be specific to the individual work. And the code we write will print all the words that are over some threshold number of occurrences, such as 2,000. Later we'll see how to print these words in order by number of occurrences, but this will be our first example. If we don't know about maps, we can solve this problem using parallel arrays or parallel array lists. And they're parallel because we'll see that words sub k, the kth value in words, occurs counts sub k times. So we have two arrays, an array of strings named words an array of ints named counts. And in our example, the with index 0 occurs 2 times with index 0. That's the parallel nature of it. And tiers with index 4 occurs 5 times with index 4. The parallel arrays, words, and counts are parallel because the same index gives the number of occurrences of the word with that index. The general algorithm here is when we read a new word, we look it up in the array of words to find its index. If we find the index, we increment the count. And if we don't find the index, that's a new word, we add it to the end. So we won't actually use arrays. We will use array lists, but we call them parallel arrays for the purpose of this example, and parallel array lists. So we'll take a look at the code that does this. You can see the URL for where this is in our course GitLab repo. For each word, we find its index. We call the .indexOf method because this is actually an array list. So words is an array list. And if we don't find it, we know it's never been seen before. We add it on line 15 to the end of the array list of strings. And we add 1, it's now occurred 1 time, at the end of the array list of int values counts. So as long as these have the same number of values, which will be initially, they're empty, every time we find a word for the first time, we add it to the end. So the index of that word and the index of its count 1 will be the same. Now, if we find the word, that means it's already occurred, we have to increment the parallel value. We found it in words with the index of stored in variable index. That happened on line 13. Now we're going to use that value on line 20 and set the value in that location to 1 more than its value. So that's the analog of counts sub k plus plus. It's a little more complicated with array lists because we have to get the value out by calling .get, and then we have to increment it by 1 and set that value. So that's counts sub k plus plus, and we have to do it that way, as we'll see on the next slide. So here is an array list. We've created the array list. We're adding some zeros to it. So we'll now have an array with 2 zeros. We can see that list.add returned true. Recall earlier in the video, we discussed that the add method for the collection interface returns a Boolean. Now I have list has 2 values in it. And what I want to do is increment the value at index 0. If I write list.get0, that's the value at index 0, and increment it by 1, I'll get an error message. It says unexpected type, required variable, found value. Now that's because the array list actually stores integer objects. Remember that array lists don't store primitive types, and integer values are immutable. It's a value. It's not a variable that you can increment. That's a subtle distinction, and it's unfortunate because with arrays, we can absolutely do that. Here's code that creates an array of 5 int values, and in Java, arrays are automatically initialized to 0. And then I simply increment the value at index 0 using code arr sub 0 plus gets 1, and we can see that successfully works. So code that works with arrays has to be slightly and subtly different, as we've seen here in this example. At the end of the code, I get the value at the index, I increment it by 1, that's a new value, and then I store that new value at the index location. So we've gone past this, and this parallel arrays means that if there are m different words, you have to look every one up. You have to scan all the words already there to determine it's a new word, because our hypothesis here is that there are m different words. Now you can increment the counter in constant time because we know where it is. Indexing, given an index into an array, is constant time. But this is going to be a quadratic algorithm because the first time there's only 1 word in the list, then 2 words, then 3 words, and finally, when we find the last of m different words, we're going to have to scan them all. So the number of words we scan to find their index is quadratic. M times m plus 1 over 2 is m squared. That doesn't scale. Quadratic is too slow. We need a new approach, and that new approach is going to be using this map class. So a map has 2 values, a map has 2 types, a key and a value. It's like the parallel arrays where we had string and integers, but these are going to be encapsulated together. We're going to associate a value with a key, and those keys will be unique. Think about the words in a file. The values won't be unique. It could be that a and the both occurred the same number of times. We're going to store the value with the key together in this map. We'll look up a value by saying, here's a key, what's its associated value? And we'll see that in the code. So here, I've created a hash map. The key is a string, that's the first type in the map, and the value is an integer. So this is another example of creating a generic variable. Its name is map, its type is HashMap string integer, and we can see in the code, I've created a new hash map. Now I'm going to read all the words in a file using scan.hasNext and scan.next because the file is uniterable, and I'm going to store 0 as the value associated with the string I just read. So what that does is, if the string has never occurred before, that's the put if absent, I'm going to store the value 0 with it. And if the string had been seen before, this code would do nothing. And the reason I'm doing that is so that this line applies to everything. Get the value associated with the string s, that's map.getS. Increment it by 1, and then store that as the value with the string s. So that code comes in a couple of pieces. It's a map, so we can call .get. Calling .get means give it a key, the string we just read. That gets a value, which is an integer, because this is a map of strings to integers. Add 1, that's a new value, a new integer, and store that integer with the string s. So that shows several examples of methods associated with maps. We can see that this put if absent code could be written as, if the map doesn't contain a key, then put the value in the map with the corresponding key s. So put if absent s0 can be written as, if the map doesn't contain the key s, put the value 0 into the map associated with s. Some people prefer to call contains key, some people prefer to call put if absent. Either one is fine. We can't, however, write the code as you see at the bottom of this slide, map.getS plus equals 1, just like we couldn't do it earlier with the array lists. We have to have the code that we see at the top, this map.getS plus 1, and then store that value in the map s. If we try to write it as you see with the red squiggle at the bottom, we get the same error message that we got with array lists. The left-hand side of an assignment must be a variable, and in this case, it's not. To iterate over all the keys in a map, you can use keySet. That method keySet gives me a set of all the keys. Internally, there's a HashSet for the HashMap class, or vice versa, depending on which one is coded first. We get the value associated with each key. That's map.get. And then in this example, we see if it's more than 2,000, in which case we print it. So this is going to iterate over every key. Now, each of the get methods is constant time, but executing all of them means we have to look at every element in the key set. That will be all the elements. So one get is constant time, but all of them will be more. There are n words. We look each one up. That's constant time. That means it scales linearly. If we read 1,000 words, that will take 10 times long as reading 100 words, and the code will take 10 times longer. The keys in the map are not ordered. not as they are in parallel arrays. We don't know anything about the order in which the keys of a hash map are stored. We'll see later with tree map that's different. The keys are immutable, they can't change. Otherwise, the locker number might change, and we don't want that to happen. So the keys have to be unique and immutable. We can loop over all the keys using keyset, and later we'll see examples that loop over the keys and the values together using a map.entry class. Here are some methods for the map class. We'll see these as we explore code in more detail. Size, get, keyset, contains key, put. We've seen those. And there's some other ones too, collected on this slide, but we'll see them as we explore coding with maps in more detail. One more WOTO. Please do it. Two computer scientists. Krista Svor, who manages the Microsoft Quantum Architectures and Computation branch of Azure. She's a distinguished scientist and the vice president of quantum software. She was a math major at Princeton with a minor in computer science and French. We think a quantum computer could possibly solve hard problems in a time frame that's more reasonable than the life of the universe, maybe a couple of years, or a couple of days, or a couple of seconds, exponentially faster. As quantum computing becomes more common, people are going to have to change encryption methods if quantum computing becomes powerful enough to solve big problems. It's not there yet. This is Donald Knuth, sometimes in computer science circles called the Donald. He is winning the Turing Award and many other awards, and he wrote this 4-volume set that you can see diagrammed at the top called The Art of Computer Programming. In many circles, he's considered the OG of computer science, both in theory and in practice. He invented LaTeX, among other things, and he has 2 quotes. If you optimize everything, you will always be unhappy, and everyday life is like programming, I guess. If you love something, you can put beauty into it. You can see him on YouTube. Enjoy.